Usually when we think about training in artificial intelligence, the instinct is to just feed it absolutely everything.
Right, yeah. More is more.
Exactly. We have this like image in pop culture of dumping the entire history of a company's database into some massive supercomputer, flipping a huge switch, and just letting the algorithm figure things out.
Which is a terrifying thought for any actual engineer.
Totally. But imagine you are building an AI to catch financial fraud.
Oh, man, yeah, a hypercritical use case. Because you're building a mathematical model that has to flag suspicious activity in real time, right? You have to catch the bad actors before the money actually leaves the ecosystem.
But here's the paradox, and this trips up almost every beginner I've ever worked with.
Hmm.
If you train that fraud detection model on literally everything,
Every single row of data.
right, all your users,
Yeah.
all their transactions, across all time periods since the company was literally founded, you are actually setting up to fail catastrophically.
Oh, 100%. It's a disaster.
Because you end up feeding it, inactive users from 10 years ago or outdated shopping behaviors and completely irrelevant technical patterns that just don't even exist in your current app architecture anymore.
Yeah, and the result of that, like kitchen sink data dump approach, is a model that suffers from severe poor generalization.
Right.
It essentially learns all the wrong lessons. It memorizes a version of reality that has already expired.
It's studying for the wrong tests.
Exactly. And when you finally deploy it into the real world to catch fraud today, in today's specific environment, it just completely collapses under the weight of its own historical baggage.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry ready and apply your knowledge to real industry projects.
Glad to be here for this deep dive.
Yeah, we are tearing down AI and ML pipelines today to figure out why feeding your model everything is, well, it's the fastest way to break it.
It really is.
Because as machine learning engineers, we constantly have to ask ourselves incredibly specific questions, right?
Right.
Like which users actually matter?
Yes.
Which time periods are relevant to the current mathematical problem? Or, with specific data points are actually going to help solve this exact use case?
And honestly, defining your data set is arguably the most consequential decision you make in any machine learning project.
More than picking the algorithm.
Oh, absolutely. It's a foundational process called filtering. And in the world of relational databases, the ultimate tool for executing this, like the foundational operation that every single data scientist and ML engineer relies on every single day, is the SQL where clause.
The where clause. So we are going to explore how to answer those massive questions about what data belongs in your model by mastering this single, incredibly powerful operation.
It really is the gatekeeper.
It is, and it sounds so simple on the surface, right?
Yeah.
Just filtering rows. But the implications for your AI's accuracy and your company's cloud computing bill are just staggering.
Right. So think back to our previous step in the feature engineering framework from Lecture 2.
The dimensionality reduction step.
Exactly. In that stage, we were looking at the raw data table and deciding which columns to keep. Because columns represent the features, right? The attributes of the entity.
Like, do we need the user's age? Do we need the device type, transaction amount?
Right. We were picking the attributes that actually have predictive power. But now the focus shifts entirely. We are no longer looking at the columns.
We're looking at the rows.
Yes. The rows represent the actual examples, the individual events, the specific people.
Yeah.
The where clause is how we define what we call the training population. It answers a really profound, almost philosophical and mathematical question, which is, what part of reality is this model actually allowed to see?
Oh, man. What part of reality is this model allowed to see? I love that framing.
It's exactly what you're doing.
Because if the data table is like the universe your AI lives in, the where clause is the tool you use to draw the physical borders of that universe.
Perfectly said.
It's like, okay, imagine you were trying to get feedback on a highly specialized piece of hardware. Let's say a new set of extreme winter snow tires.
Okay, I like where this is going.
You wouldn't conduct a survey by asking people who don't even have a driver's license.
Obviously not.
And you definitely wouldn't include survey data from people who live in a tropical climate where the temperature never drops below like 70 degrees.
Right.
You would create a highly specific, targeted focus group.
Right, because you are deliberately excluding data that, while technically valid, I mean, it's factually true in the real world, is completely irrelevant to the specific task you're trying to optimize for.
Right.
Like, a tropical driver's opinion on snow tires is technically valid data about their preferences, but it introduces massive noise into your specific engineering problem.
It's like having a strict bouncer at an exclusive club.
A very strict bouncer.
The club is your machine learning model. There's this massive line of data rows outside, stretching around the block. We're talking billions of rows in a modern enterprise system.
Oh yeah, easily.
But the bouncer, the where clause, has a very specific VIP list. If a row of data doesn't meet the strict criteria, it just doesn't get past the velvet row.
Nope, denied entry.
But I do want to introduce a legitimate data science dilemma here, because I think a lot of people learning about AI, so especially those of you with like a basic Python background who have built maybe a simple linear regression or two,
Sure.
you might be thinking, wait a second, aren't deep learning models famous for needing massive data sets?
The whole big data thing.
Exactly. If we start aggressively filtering out, say, all our inactive users, doesn't our model never learn what an inactive user looks like? Are we intentionally introducing survivorship bias into our training data by throwing all this away?
That is a phenomenal question, and it really strikes at the heart of experiment design, because there is a massive difference between representative sampling and task-specific scoping.
Okay, unpack that a bit.
So when we filter data for a machine learning model, we are not trying to create a perfectly balanced census of the entire world. We are trying to isolate the specific decision boundary the algorithm needs to learn. If your model's job is to predict which currently active users will buy a premium subscription next month,
Then data from users who deleted their accounts 5 years ago provides zero signal.
zero. It only provides noise. The more data is always better. Myth only really applies to relevant data. In machine learning, quality absolutely beats quantity every single time.
That makes total sense.
If you have 100 million rows of garbage or irrelevant contexts, your model will just become very, very confident at predicting garbage. By filtering, we are actively improving the signal-to-noise ratio.
We are stripping away the static so the algorithm can actually hear the music.
Yes.
Let's visualize the mental model of the data table again, just to anchor this for everyone. When we selected columns in the previous step, using the select statement, we were reducing the data horizontally.
Right, making the table narrower.
Narrower, exactly. When we apply a where condition, when we set up that gatekeeper, we are reducing the vertical size of the data set. We are stripping out the rows. Millions of raw rows flow down from the source system. They hit that where condition, and only the relevant rows, say transactions over $100, or users who have logged in this specific month, make it through to the model's training set.
It's a vertical slice of reality.
A vertical slice of reality. Okay, that establishes the why. We want high signal, low noise. We want a clean, relevant universe for our AI to learn from. So how do we actually give this gatekeeper its instructions?
Now we get to the fun part, the code.
Yeah, let's ground this in a real scenario. Instead of just walking through a list of SQL textbook operators, let's play detective.
Ooh, I love a good data mystery.
Let's say we are ML engineers at a massive e-commerce platform, and we've just been hit by a highly sophisticated distributed fraud attack.
Right.
We have a transactions table with, say, 5 terabytes of data from the last decade.
That's a lot of rows.
A massive amount. We need to isolate the exact footprint of this attack to train a new model to catch it. How do we start?
Well, we have to translate our business logic into SQL syntax. For those of you who have written Python, you've probably used pandas, right?
Yeah, the classic data frames.
You might have done something like data frame amount 100. SQL is actually much closer to plain declarative English.
It's very readable.
Very. The basic structure of any SQL query trying to filter data is select columns from table where condition.
It reads almost exactly like a sentence.
Yeah.
Select usered amount from transactions where amount 10,000. Let's say we know this fraud ring is only targeting high-ticket items. We apply that rule.
And that condition amount 10,000 is a logical test. The database engine is going to look at every single row and evaluate that mathematical statement.
And if the answer is true,
If it's true, the row passes the bouncer. If the answer is false, the row is discarded from the result set, completely dropped.
but a sophisticated fraud ring isn't just defined by one variable, right? We rarely have just one rule for the bouncer.
Rarely. Usually it's a very complex set of conditions.
So we know this specific attack is originating heavily from specific regions, but they are using VPNs to bounce between a few countries. Let's say we need to narrow our massive terabyte table down to high-ticket transactions that are coming from either a specific high-risk region or an unusual proxy server hub.
Ah, okay. This brings us to the essential logical combiners, ND and OR.
The absolute basics of logic gates.
Exactly. These are the fundamental building blocks of complex filtering logic. And DOM means that every single condition you list must be strictly true for the row to be included.
It's highly restrictive.
Very restrictive. If you write where amount 10,000 ND country or region, you are demanding that both things happen simultaneously.
So if a transaction is for $20,000, but it's from region B,
It fails the test. It gets dropped. And if it's from region A but it's only for $50, it also fails.
both forms of ID are required by the bouncer.
Exactly. It shrinks the dataset rapidly.
But what about OR? Because we know the attackers are bouncing between region A and region B.
Right, or is expansive. It means that if at least one of the conditions evaluates to true, the row gets a pass.
Okay.
So you might write where country is region A or country is biased region B. As long as the user's IP is mapped to one of those two places, they are included in our training data.
Got it. Let's build out our detective query then. We want high-value transactions from a whole list of suspected VPN proxy countries. I could write, where amount 10,000 day, and then I open some parentheses, country X or country Y or country Z.
You could.
And I could just keep chaining these OR statements together forever for all 20 countries on our watch list. But
Yeah.
from an engineering perspective, that feels incredibly clunky.
It's awful to read. Yeah.
In Python, we'd probably check if a value is in a list or a dictionary. Is there a cleaner way to handle this in a database?
Yes, thankfully. A critical tool for keeping your code readable, maintainable, and frankly professional is the IN operator.
The IN operator.
Yeah. Instead of endless OR chains, you filter using sets. You simply write where country in, country X, country Y, country Z.
Just in, followed by parentheses with your list of acceptable values.
That's it.
It's essentially checking, does the value in the country column exist inside this predefined set I just provided? That is so much cleaner.
It's mathematically equivalent to chaining all those OR statements, but it is vastly superior for code maintenance.
Oh, for sure.
Imagine another engineer on your ML ops team comes along to read your code 6 months from now. A clean AND statement immediately communicates your intent. It says, here is the allowed list of categorical variables.
Plus, doesn't it run faster sometimes?
Good catch.
Yeah.
Yes, furthermore, some database query optimizers can actually handle IN lists more efficiently under the hood than a massive string of OR conditions, especially when dealing with indexed columns.
Wow. Okay, so we've got our high-value targets. We've got our geographic footprint locked down with the IN operator. Now let's talk about the timeline.
Ah, time. Always the trickiest part.
We know this specific fraud ring started probing our network in a very specific window. Let's say exactly during the second quarter of the year. I want to grab transactions between April 1st and June 30th.
Okay.
I could write where transaction date equals 2024-04 or 01 and transaction date equals 2024-0630. That works mathematically, right?
You absolutely could do that, and it is syntactically valid. But again, SQL provides a dedicated, highly readable operator for this exact scenario.
Which is?
Between, you can simply write where transaction date between 2024-0401 and 2024-0630.
Between. It's so intuitive. And I imagine it prevents you from accidentally messing up your greater than or less than signs, which is like a classic source of human error.
Oh, the amount of times I flipped an alligator mouth the wrong way. It's embarrassing. Between saves you from that.
Quick question, though. Does it include the endpoints? Like, if a transaction happened exactly at midnight on April 1st, does it get included?
Yes. Between is strictly inclusive. It grabs the endpoints.
Good to know.
That is a subtle but vital detail to remember when you're defining your training windows. If you only wanted data up to a certain date but not including it, you would need to revert to using the strict less than operator.
Okay, our data set is shrinking rapidly. We're really zeroing in on the attack. High value, specific countries, specific time frame. But here is the trickiest part of this specific fraud ring.
What are you doing?
They are using algorithmic email generators to create fake accounts. The emails always look like a completely random string of characters, but we noticed a pattern.
Oh, there's always a pattern.
Because of the specific software they're using to bypass our security, their fake emails always end with a very specific obscure domain. Or they always have the word verify injected somewhere in the middle of the string.
Ah, sloppy algorithm design on their part.
Exactly. But how do we filter for messy text patterns? I can't just say where email verify, because their email is actually john.verify.doe@weird-domain.com. It's not an exact string match.
No, an equal sign won't work there at all. This is where pattern matching comes in. In SQL, the operator we use for text pattern matching is like, but like on its own isn't quite enough. We have to pair it with wildcards. The most powerful and common wildcard is the percent symbol.
The percent symbol. So
Yeah.
what does that actually command the database engine to do when it's scanning the rows?
You can think of the percent symbol as representing any sequence of characters or even no characters at all. It is a totally dynamic placeholder.
Okay, so if you want to catch any email ending in that obscure domain,
You would write, where email like percent at weird-domain.com.
oh, it literally translates to, I don't care what the string starts with, that's what the percent sign means, but it absolutely must finish with the exact literal characters at weird-domain.com.
You nailed it. And the placement of that wildcard completely changes the execution logic.
How so?
Well, if you wrote fraud percent with the percent at the end, it means the string must start with fraud, and I don't care what comes after. If you put the percent sign on both sides, like percent verify percent, it commands the database to search for the exact word verify anywhere inside the text, regardless of what precedes or follows it.
I want to pause here. I really want to dig into the engineering consequences of what you just said.
Oh.
Because earlier, I mentioned the difference between a beginner writing code that just works and an engineer writing code that actually scales in production.
That's very true.
Let's say I write a query with a leading wildcard, where email like the tens verify percent, and I run that on a table with a billion rows. What actually happens under the hood in the database?
Yeah, you've just hit on one of the most critical performance bottlenecks in data engineering.
I knew it.
To understand why like percent verify percent is so dangerous, you have to understand how databases search for data. Databases use data structures called B-trees to create indexes. It's very much like the index at the back of a massive textbook.
And the index is sorted alphabetically.
Exactly.
So if I'm looking for an email that starts with the letter A, the database doesn't read the whole book. It just jumps straight to the A section in the index. That's incredibly fast.
Incredibly fast. If you write where email like Alex percent, the database can use the B-tree index. It jumps to the A's, finds Alex, reads those specific rows, and ignores the rest of the billion rows. It's a highly optimized operation.
But if you write where email like percent verify percent,
The wildcard is at the very beginning.
so the first character could be anything, an A, a Z, a number, a symbol.
Yep. Because of that, the database cannot use the alphabetical index. The index is entirely useless to it.
Oh, wow.
So the database engine is forced to perform what is called a full table scan. It literally has to open up and read every single one of the 1 billion rows, character by character, to see if the word verify is hidden somewhere inside.
And a full table scan on a massive cloud database consumes a tremendous amount of compute power.
It is brutal.
It spikes the CPU, it hogs memory, and it can literally cost the company thousands of dollars just to run that single query if you put a percent sign at the front of the string.
This right here transforms a basic syntax lesson into a high-level engineering insight. A data scientist might write that query to get their subset for a quick EDA, but an ML engineer knows that running that in a daily automated pipeline will crash the system or blow up the cloud budget.
You have to understand the mechanical consequences of the filters you apply.
Exactly. It's not just about getting the right rows, it's about how you get them.
That is a brilliant distinction.
Yeah.
Okay, let's go back to our detective story. We've applied our complex filters, but we hit a snag.
Okay, what's the snag?
We know the fraud ring uses stolen credit cards, but they intentionally bypassed the billing address field in our checkout flow because, say, our legacy system allows it.
Ah, legacy systems, always a loophole.
Right. The billing address field is just completely empty for these fraudulent transactions.
Yeah.
So I go into my SQL console and I write where billing address NLL. I hit execute.
And let me guess.
The query runs perfectly. No syntax errors at all. But the result set comes back totally empty, 0 rows returned. Even though I know for an absolute fact there are thousands of these fraudulent transactions in the database with an empty billing address.
Yep.
I spent 3 days debugging a pipeline last year because of this exact issue. It failed completely silently. What is the database doing here? Why can't I just use an equal sign for NLL?
Welcome to the NL trap.
The NLL trap.
It is a rite of passage for every data professional. I've been caught in it. You've been caught in it.
It's the worst.
To understand why your pipeline failed silently, we actually have to talk about epistemology.
Wait, philosophy?
Yes, the theory of knowledge. and how relational databases interpret the very concept of NLL. Because in SQL, NLL does not mean zero. It does not mean an empty string.
What does it mean?
NLL fundamentally represents an unknown value. It literally means we have no idea what is in this box.
It's an epistemological void. It's not a value, it's the absence of a value.
Exactly. So when you write billing address equal less and NLL, you are asking the database a logical question. Is the value in this row equal to an unknown value?
Okay, I see where this is going.
The database engine evaluates this. Since it doesn't know what the unknown value is, and it doesn't know what might be missing, it cannot logically answer, yes, they are equal, which would be true. And it cannot logically answer, no, they are not equal, which would be false.
Because it just doesn't know.
Right. It can only evaluate the statement as unknown.
Because if I have two mystery boxes, right, and neither of them has a label, I can't say for sure that the contents are identical.
Perfect analogy.
They might both contain an apple, making them equal. One might contain an apple and the other an orange, making them unequal. The mathematical truth of their equality is inherently unknown.
You've just perfectly described three-valued logic. SQL operates on true, false, and unknown. Here is the mechanical catch that caused your bug. The where clause gatekeeper only allows a row to pass into the result set if the condition evaluates strictly and definitively to true.
So if the result is false, the row is dropped.
Yes.
And if the result is unknown,
the row is also dropped.
that is why the bug is silent. The query didn't crash because the syntax was perfectly legal, but the database evaluated NL equals N, all L as unknown. And the where clause just silently swept all those thousands of rows into the digital trash can.
Into the void.
So what is the correct architectural way to capture these missing values for our fraud model?
Because NL is a state of being rather than a concrete quantifiable value, you cannot use the standard mathematical equals sign. You must use the specific operator ISNN.
AIML.
Yes. You are asking the database, is the state of this field currently unknown? So the correct syntax is where billing address is NL. Or conversely, if you only want complete data where the user actually provided an address, you use I is not NL.
I is NL. It's such a tiny syntax change, but fundamentally it's a completely different philosophical question you're asking the compute engine.
Right.
Are you in a state of emptiness versus are you mathematically equal to emptiness?
It changes everything.
And this is huge for ML, right? Because handling missing data, deciding whether to drop rows where a critical feature I's in L, or whether to keep them and perhaps impute those NLs with median values, that is a massive part of the feature engineering process.
Absolutely. Your where clause is the front line of that entire missing data strategy.
Okay, we've successfully navigated the detective story. We've built a robust syntax toolkit. We've mastered logical combiners like AND and OR, set filters with IN, range filters with between, text pattern matchers with like and wildcards, and we survived the NL trap using ISNL.
We covered a lot of ground.
We really understand the mechanics of how to filter. But let's zoom out again. Let's transition from the mechanics of SQL to the actual machine learning strategy.
Good idea.
Because filtering isn't just about writing code that successfully executes. It's about designing the experiment your algorithm will actually learn from.
Designing the experiment, yes. I want you to really internalize that phrase. A machine learning model doesn't possess innate knowledge about the real world.
Right. It's not magic.
It only knows the specific limited universe you show it. If you apply different filters to your raw data, you create completely different data sets. And those different data sets will yield radically different AI models with entirely different behaviors and blind spots, even if you use the exact same algorithm architecture.
Which brings us to the most dangerous part of designing that experiment. What is the biggest, most catastrophic trap an ML engineer can fall into when drawing the boundaries of their data set?
Without a doubt, the most critical concept to master is temporal filtering. In machine learning systems, time is the ultimate dimension. How you handle time matters more than almost any other attribute in your data.
Temporal filtering. So we're talking about the flow of time in our data table. Say I want to train a model to predict user behavior for the upcoming year. I might introduce a filter like where transaction date equal 2024-0101 to ensure only recent data is used.
Right.
But why is the timeline so dangerous? What actually happens to the model if I mess up the chronological order?
If you fail to properly isolate the timeline, you will run headfirst into one of the most fatal mistakes in the entire industry: data leakage.
Data leakage.
Oh.
Okay, let me float an analogy to see if my mental model is aligning with the engineering reality.
Go for it.
Let's say I'm a university professor, And my machine learning model is a student taking a final exam. The goal is for the student to learn the course material by studying past examples, doing homework, and then be able to generalize that knowledge to answer brand new, unseen questions on the final test.
A perfect representation of the training and inference phases.
Is data leakage basically like accidentally leaving tomorrow's answer keys sitting on the student's desk while they're studying for today's test?
Exactly.
They memorize the specific answers, they completely ace the test, they look like an absolute genius on paper, but they didn't actually learn the underlying concepts, they just memorized the future.
That is precisely what data leakage is. It happens when information from the future information that would absolutely physically not be available at the exact moment the model has to make a real-world prediction somehow bleeds backwards into the training data set.
What does that look like in a real production environment? Because I want to move beyond like hypothetical churn models.
Right.
Have there been massive real-world catastrophes caused by data leakage?
Oh, absolutely. Tons of them. One of the most famous examples in the medical AI field occurred with a data set designed to predict the mortality risk of patients with pneumonia.
Okay.
The goal of the model was to look at a patient's initial symptoms and medical history upon arriving at the hospital, right? And predict whether they were at high risk of dying so doctors could triage them effectively.
Sounds like a perfect use case for machine learning. Look at the historical data, find the patterns of who survived and who didn't.
Right. So they trained the model on a massive database of historical patient records. The model performed incredibly well in testing, off the charts. But when the researchers started analyzing the specific rules the algorithm had learned, they found something completely horrifying.
What was it?
The AI had learned that if a patient had a history of severe asthma, their risk of dying from pneumonia was actually lower.
Wait, what?
Yes. The model was going to recommend sending asthmatic pneumonia patients home, classifying them as low risk.
That makes zero medical sense. Asthma is a severe respiratory condition. Pneumonia attacks the lungs. And asthmatic with pneumonia should be the highest possible risk category. Why on earth did the algorithm learn the exact opposite?
Because of data leakage embedded in the hospital's historical processes.
Oh.
Think about it. In the real world, historically, when an asthmatic patient arrived at the hospital with pneumonia, the triage doctors knew it was a massive emergency.
So they acted fast.
They immediately bypassed the waiting room and sent those patients straight to the intensive care unit.
Huh.
Because those patients received aggressive, immediate, top-tier medical intervention, their actual historical survival rates in the dataset were exceptionally high.
Oh, wow.
Yeah.
The model looked at the data and saw asthma equals survival. It didn't know about the ICU intervention.
Exactly. The fact that they were admitted to the ICU was a future event relative to the moment of admission, but the model was inadvertently trained on the outcome of that future intervention.
Because it was all in the same historical row of data.
Right. If they had deployed that model, it would have killed people because it would have told the triage desk not to worry about the asthmatics, denying them the very ICU care that historically saved their lives.
That is terrifying. It learned a completely spurious correlation because the timeline of events wasn't strictly enforced.
It happens all the time.
I heard another one from the early days of the COVID-19 pandemic.
Oh, the chest x-ray one.
Yes. A bunch of different research teams rushed to build AI models that could diagnose COVID by looking at chest x-rays. They scraped data from multiple hospitals. The models achieved like 98% accuracy in the lab.
But when they tested them in the real world,
They failed completely.
I know exactly the case you're talking about. The classic confounding variable.
The AI wasn't looking at the lungs at all. The researchers realized that the data from the hospital with the severe COVID cases had a specific text font printed on the corner of the X-ray machine's digital output.
And the healthy patients.
The data from the hospital with the healthy patients used a different font.
Unbelievable.
The deep learning model, which is fundamentally just a lazy pattern matcher, figured out it was way easier to just read the font in the corner of the image to predict the diagnosis than to actually analyze complex lung tissue. It memorized the source of the data, which acted as a proxy for the label.
Both of these examples highlight exactly why strictly enforcing boundaries on your data is a matter of life and death for your model. If you don't use your filtering tools to rigidly define what the model is allowed to see, it will cheat.
It will take the path of least resistance.
Every time, it will find the easiest path to minimizing its error function, even if that path is logically absurd.
So how do we use our SQL toolkit, specifically the where clause, to stop this timeline cheating?
We use the where clause to establish a rigid training cutoff. This is the core mental model you need for temporal integrity. Past data is used for training. Future data must be strictly quarantined. There
Ooh.
must be a hard, mathematically impenetrable wall between them. The where clause acts as your SQL guardrail enforcing that wall.
A SQL guardrail. So if the moment of prediction is, say, midnight on December 31st, I would write something like, where event timestamp 2023 12/31 23.59.59 time.
Exactly.
And that strictly forces the database to only feed the model information that was recorded prior to that exact second. It enforces an absolute chronological barrier.
Yes. If you visualize a timeline running from left to right, you have your past data, then a vertical line which represents your training cutoff, and to the right is your future data, the outcomes you're trying to predict.
Right.
You put a big green check mark over the past data and a massive red X over the future data. The where clause is the tool that physically draws that vertical line in the database.
That makes perfect sense.
It guarantees that the model has to learn the hard way without accessing the answer key, which is the only way it will develop patterns robust enough to perform in the real world.
That is such a vital concept. It's not just about filtering out noise. It's about physically preventing the algorithm from cheating the timeline. But here's where we pivot a bit, because filtering early at the database level doesn't just make the model smarter and stop it from cheating.
No, it does much more.
It also has this incredible hidden superpower when it comes to the pure engineering and infrastructure side of things. It makes the whole architectural system significantly cheaper and exponentially faster.
This is where we shift our hats from data science thinking to data engineering thinking.
I love this part.
In modern enterprise tech stacks, we are usually dealing with massive cloud data warehouses. Think platforms like Google BigQuery, Snowflake, or AWS Redshift.
The heavy lifters.
Right. These systems hold petabytes of data, and they operate on a very specific pricing model. When you run a SQL query, those systems have to spin up massive distributed compute clusters to read that data off the disk.
And they charge you based on the resources you consume.
Exactly.
Right. It's not like running a script on your local laptop where the electricity is basically free. Cloud providers charge you based on how much data you scan, how much memory you allocate, and how much CPU time your query takes to execute.
So if you don't filter your data early in the pipeline, you are paying the cloud provider real dollars to scan, load into active memory, and process millions of rows of data that you are ultimately just going to throw away later when you load it into your Python environment anyway.
That's just throwing money out the window.
Hmm.
Let me upgrade an analogy here to really drive this home. Think about the logistics of a major delivery service. Let's say you run a restaurant and you need to order ingredients.
Okay, I'm tracking the supply chain.
You order 1,000 pounds of vegetables from a farm. The shipping company charges you based on the weight of the cargo loaded into the truck. They charge you 50 cents per pound for the entire journey from the farm to your restaurant.
Simple enough.
Now let's say half of those vegetables are spoiled or are the wrong type, and you know you're just going to throw them in the dumpster behind your restaurant as soon as they arrive.
A massive waste of resources.
Not filtering early in SQL is exactly like telling the farmer to load all 1,000 pounds of vegetables, good and bad, onto the truck.
Oh, wow. Yeah.
You pay the shipping company for the full weight. The truck burns fuel, carrying it across the country. It arrives, you spend labor hours unloading it into your kitchen, and then you sort it and throw 500 pounds in the trash.
You expended all that physical energy, labor, and money-moving cargo you didn't even want. That is a perfect representation of compute costs. You paid for the scan.
Whereas filtering early, using a strict where clause right at the source database, is like having an inspector at the farm sort the vegetables before they ever get loaded onto the truck.
Exactly.
You leave the spoiled ones at the farm. You only load the 500 pounds of good vegetables. The truck is lighter. The shipping fee is cut in half. The fuel cost is lower. And you don't waste any labor unpacking garbage at your restaurant.
And in the cloud computing world, that energy and compute time directly translates to money. Professional engineers understand the architecture of these systems. Modern columnar databases like Snowflake or BigQuery store data in what we call micro-partitions.
Micropartitions.
Yeah. If you put a where clause on a date column, like where event date equals 2024-01 at 01, the database optimizer is smart enough to completely skip reading the micropartitions that contain older data.
Really?
Yes, it doesn't even load them off the hard drive.
So by writing that one line of code early in the pipeline, you bypass the disk read entirely.
That single line of declarative logic slashes the rows processed, it plummets the memory usage, and drops the query cost significantly. It literally turns a $10 query into a 10-cent query.
And when you're running automated ML pipelines every day, every hour across thousands of tables, that architectural efficiency adds up to hundreds of thousands of dollars in savings for a company.
It really does. It's massive.
So the where clause is a budget saver just as much as it is a model saver. But wait, there is one more hidden superpower of this exact filtering logic, isn't there? Something that connects the very beginning of the data prep pipeline directly to the end mathematical goal of the AI.
Ah, yes. And this is a really advanced machine learning insight that bridges the gap between raw data engineering and model training.
Let's hear it.
The exact same foundational logical structure we use to filter data in the where clause is later used to create the target variables.
The labels.
Yes, the labels that the AI is mathematically optimizing to predict.
Let's unpack this carefully because this is where the puzzle pieces really snap together. The label is the answer we want the model to learn to guess, right? In supervised learning. Like, is this transaction fraudulent? Yes or no? Or is this a picture of a hot dog? Yes or no?
Exactly. The algorithm needs an objective truth to compare its predictions against so it can calculate its error and adjust its internal weights. But where do those labels come from? In a massive structured data set. They don't just magically appear out of thin air. We, the engineers, have to define them using complex business logic.
Let's go back to our e-commerce example. Say the business stakeholders come to us and say, we want an AI to predict which newly registered users are going to become high-value customers in their first year.
A classic predictive lifetime value problem. So the AI needs a historical label that explicitly states whether a past user was high value or not, so it can study their early behavior and learn the mathematical pattern that leads to that outcome.
Right.
But what defines high value? The algorithm doesn't know what that English phrase means.
The business might define high value as any user who has spent more than $500 total.
Okay.
Now think about the logic here. If we just wanted to filter our table to only look at those users, we use the where clause, where total spent 500.
Right. That logic restricts the data set. But if we want to create a mathematical label for the AI to predict, we use that exact same logical statement, total spent 500, and we embed it inside a conditional transformation to create a brand new column.
How does that look in SQL?
In SQL, and you can map this directly to a pandas apply function in Python, we use a case when statement.
Oh, I see the pivot. So instead of throwing the other rows away, we keep all the users in the data set, but we flag them based on the condition.
Exactly.
We would write something like, case when total spent 500, then 1 else 0 end as an issue value.
Precisely. That transforms your basic declarative filtering logic into a binary mathematical label, a 1 or a 0, that a machine learning algorithm's loss function can actually process.
That is amazing.
The core condition total spent 500 is the absolute ground truth. Used in a where clause, it acts as a gatekeeper, discarding rows. Used in a case when statement, it becomes the target variable.
The very objective function the AI is being trained to optimize for.
It connects the foundational data filtering syntax directly to the creation of the model's entire purpose.
That is such a cool mental pivot. The mathematical logic remains identical. It just depends on whether you are using it to define the boundaries of your experiment, filtering the input, or the goal of your experiment, labeling the output.
It's all connected.
We have covered a massive amount of ground today. We've gone from basic syntax to cloud infrastructure to the epistemology of missing data.
It's been a journey.
Let's do a quick mind map summary to anchor exactly where we are in the grand scheme of feature engineering.
It is essential to continuously zoom back out to the macro pipeline view so these concepts don't just float in isolation.
Step 1 of our SQL feature engineering framework, which we covered in Lecture 2, was projection. That was taking the raw source tables and using select to choose the specific columns, making the data narrower, reducing the dimensionality.
Correct.
Step 2, which is what we mastered today, is filtering, using the where clause to select the specific rows, making the data shorter, isolating the sample space.
And that filtering step determines the exact population of rows that are authorized to continue forward into the subsequent stages of the pipeline. You are taking billions of raw, chaotic, noisy events and deliberately distilling them down into a high-signal, relevant population.
You now know the syntax and the strategy to build a highly targeted, mathematically clean dataset. You can isolate active users. You can grab only high-value transactions. You know how to use temporal logic to prevent the catastrophic failure of data leakage.
The guardrails.
Yes. And you know how early filtering saves your company massive amounts of compute budget. You have the power to define the physical universe your AI will learn from.
But as any working engineer will tell you, the real world is incredibly messy. Up until now, throughout this entire discussion, we've been operating under the assumption that all your necessary data lives neatly inside one single table.
Oh, right.
But in any real industry project, that is practically never the case.
Right. A modern enterprise architecture is highly normalized. Customer demographic data, like their region and sign-up date, is sitting in a user's table. But the actual monetary things they bought are over in a completely separate transactions table.
And maybe their website browsing behavior, the clicks and page views, are in a massive streaming events table.
Exactly. Data is siloed. Now you know how to select columns and filter rows from a single, isolated table. But the next massive architectural challenge for an ML engineer is, how do we stitch these disparate pieces of reality back together?
Right.
How do we combine multiple separate tables into one single, unified, wide data set for the machine learning model to consume?
And that is exactly what we are going to tackle next. In the next lecture, we break the single table limitation and we learn the absolute powerhouse of relational databases, the JON.
But before we get there, you need to solidify what you learned today. To really build that mental model, you can't just listen, you need to practice.
Theory without application fades quickly. Muscle memory is where the learning actually becomes permanent.
Try today's filtering exercise for yourself. Get your hands dirty writing some complex where clauses if you get stuck, or if you have questions about how B-tree indexes react to wildcards, or if you want to debate the philosophical implications of temporal leakage, write your questions in the comments below.
We love seeing how you guys tackle these concepts, and we read through them to see what you're building.
We really do. And of course, to keep building your industry-ready ML skills, make sure to like, share, and subscribe to 60 Seconds Academy.
Because every step of this engineering pipeline builds sequentially on the last. You cannot join tables properly and efficiently if you haven't filtered them correctly first.
So true. See you in the next deep dive. But before we go, I want to leave you with a final provocative thought.
Ooh, okay.
Think back to that fraud detection AI we talked about at the very beginning of this conversation.
The one that was trained on the decade-old data.
Right. The one we successfully saved by filtering out the outdated data. We built a perfect temporal wall. We improved the signal. But machine learning is not a static endeavor. It is a constant mathematical arms race.
That's the reality of the industry.
What happens when the highly sophisticated fraudsters realize you are filtering for recent data, and they intentionally alter their algorithms to disguise their new attacks so they look exactly like the outdated, inactive users you just filtered out of your training set?
Oh, that happens.
This is a phenomenon known as adversarial machine learning, driven by concept drift. If the reality of the threat adapts to hide inside your blind spots, who really defines the boundaries of your AI's universe then? You, or the malicious actors dictating the data you chose to ignore? Think about how your filtering logic must evolve over time to survive.